Hi everybody, in this video we're going to look at how depth first searches, DFS, and breadth first searches, BFS, explore a graph. These searches will show us how to build spanning trees in two different ways. So why would we need these kinds of searches? When we're working with graphs, we often need a systematic way to visit all of the vertices. Simply moving randomly through the graph can lead to missed vertices or repeated paths. Using a search method gives us a consistent way to explore the graph, which is where our two approaches, DFS and BFS, come in handy. To show you an example of using the algorithms, I'm going to use the graph below, and in each case I'm going to start at vertex A. Remember, our goal is to form a spanning tree, which means we have a set of edges that connect every vertex, but we won't have any cycles. We'll only have one path between any two vertices. For the 8 vertices we have, we know we're going to need 7 edges. The search is going to help us pick which edges we should use in our tree. We'll start with the depth first search, DFS. For DFS, we're going to follow one path as far as we can, which means in this case we're going to start at A and walk to an unvisited neighbor. From there, we're going to keep diving deeper, one edge at a time. If we get stuck, we'll back up to the last vertex and choose another option. We'll repeat this until every vertex has been reached. Our answer is going to be a graph. We're not going to write out the series of vertices. So let's jump in and get started. We're going to start our deep dive from A. We'll go from A to B, then from B we'll go to E. E looks like it could go to C or to G. When you have those cases, stick with either alphabetical or numerical order, depending on how you've labeled your vertices. In this case, we want to go to C because C comes before G in the alphabet. From C, we can't go to A because that would form a cycle, so instead we're going to go to F. From F, we should go to D, but here we get stuck. We have a dead end. Because we have nowhere to go, we have to backtrack, so we're going to go back from D to F. Now that we're back at F, we're ready to finish up our graph. We'll go from F to G, and then G to H. Now we've been through every vertex, we don't have any cycles, and we have a nice spanning tree. Now let's find a spanning tree using the breadth first search. A breadth first search explores the graph layer by layer. So we're going to start at A, which is layer 0. Then we're going to visit all of A's neighbors. That's level 1. Then we'll take every new vertex one step further out. We're going to continue this layer by layer until all layers have been reached. So layer 1 says we visit all of A's neighbors, which are B, C, and D. Now we're ready to go to layer 2. So we're going to look at these vertices B, C, and D and try to take them one step further out. B is going to go to E, C is going to go to F, but D can't go any farther. If we include the edge from D to F, we form a cycle, so we know that D is done. We're also not going to include the edge from C to E because it once again forms a cycle. Now we're ready to move on to layer 3. That means we're extending out from E and F. E is going to go to G, F is going to go to H, and at this point we've used all the vertices, which gives us another spanning tree. Let's take a quick look at the comparisons between our two spanning trees. As you can see, one graph gave us two different spanning trees depending on the algorithm we used. So we have the same graph and the same starting vertex, yet the two searches gave us different edges in the spanning tree. DFS forms one deep branch where BFS spreads out into shallow layers. Let's do that again. This time we have 10 vertices and 15 edges, so this is nearly twice the size. This time our spanning tree has 9 edges. Instead of labeling the vertices by letters, I've labeled the vertices by numbers. We're going to start our searches at vertex 1, and we'll use both DFS and BFS to find our spanning trees. Using DFS, we're starting at 1 and we're going to take a deep dive into the edges. We'll go from 1 to 2. 2 could go to 4 or 5, so we're naturally going to go to the lower number of 4. 4 has to go to 8, 8 has to go to 9. When we get to 9, we see 3 edges. We have 5, 6, and 10. We're going to go to the smallest number, which is 5. At 5, we can't go to 1 because that creates a cycle. The same thing would happen if we tried to go to 2. That says we have to move over to 6. From 6, we want to go to 3, which will lead us to 7, and then let us finish at 10. This time we have one long path through all of the vertices and we didn't have to back up at any point. Now let's use BFS for the same graph. We'll start at vertex 1 and form our first layer. That's going to go to 2, to 5, and to 3. Forming our next layer, it's easy to see that 2 is going to go to 4. We can't connect 2 to 5 because that would form a cycle. 3 is going to go to 6 and to 7. 5 can't connect to 6 because that would form a cycle, which means we're going to have 5 connected to 9. Layer 3 will connect 4 to 8 and 6 to 10. Now we've covered all the vertices and made a nice spanning tree. Again, let's compare our results. Even on this bigger graph, the pattern holds. DFS keeps one long winding branch while BFS fans out into shallow layers around the starting vertex. As a quick wrap up here, things to remember. DFS is our deep dive into a graph. We're following a path as far as we can. If we get stuck, we back up and then look for a continuing path to follow. BFS goes wide. This means we're exploring one layer at a time, reaching near vertices first. This produces a shallow, spread out spanning tree. Remember, both algorithms are going to span the graph. That means they each visit every vertex once and select the needed edges to produce different trees that are both valid.